I would like to welcome Professor Rinner to deliver this very interesting talk on self-aware systems. Professor Rinner is with the Alpen Adria University in Klagenfurt. He was in the past with the Graz University of Technology. He leads the pervasive computing group there at this university, and he initiated an Erasmus Mundus joint doctorate program on interactive and cognitive environments. So Bernhard, you can start.
Okay, so welcome to this talk on self-awareness for autonomous systems. Before we go into the details of this talk, let me just briefly summarize the objectives of this talk. So the main objective is that I'd like to introduce self-awareness, in particularly from a computational context. As we will see throughout the talk, self-awareness is a very broad concept. So what I will do is I will summarize some key concepts and about architectures and capabilities of self-aware systems. I will sketch a few examples and case studies. And also I'd like to discuss some open challenges, because I do think there are important open challenges. And I do think, since the main audience here is junior researchers, that could be inspiring for identifying new research topics for you. So I also want to make it clear that this talk is not about a comprehensive explanation of a specific approach. It's more like an overview. Okay, so let's start. We all know autonomous systems, and what you see here on this slide is this famous architecture of an intelligent agent taken from an AI textbook. So here, the main idea of this intelligent agent is that it performs continuously a sense process act cycle in order to process data the agent receives from the environment and gain information and learn experiences from this data in order to issue appropriate actions and in order to interact with the environment. Typically, this reasoning of the agent is based on models. Right? These models can be provided a priori in some cases, in rare cases, where many of the environments, many details of the environments are known. In many cases, these models need to be improved, acquired, learned over time from the experiences the agent makes. And it's also quite natural that autonomy of the agent is strongly influenced by the models and the capabilities of the agent itself. In particular, about what resources are available and what are the reasoning capabilities of such an agent. The prototypical application of such an intelligent autonomous concept or autonomous agent is robotics. And we have seen many implementations of this concept in the robotics domain. A more recent application domain is about collective systems. So here we are talking about networks of autonomous systems. And this group or these collections of autonomous systems can then either operate rather independently on each other or strongly collaborate in order to achieve specific goals and objectives. So also these agents perform then this sense process act cycle. However, they also do some communication so that they exchange information among themselves. And there are also many applications for these networked autonomous systems. You can name it. This could be cyber-physical systems, Internet of autonomous things, swarm robotics, just to give a few examples. Also, a few notes about self-awareness in the beginning. So self-awareness is a very broad concept, and it's borrowed from different disciplines, mainly from psychology and cognitive science, where this concept were introduced to understand human reasoning better. This concept is mostly described by specific capabilities of biological or artificial agents. And the very important aspect of self-awareness is that these capabilities also include some representation, some knowledge about the agent itself. So the knowledge about the state of the agent, the models of the agent is made here explicitly available. The knowledge the agent acquires over time may take on different forms, and naturally this depends on the kind of perception the agent performs, and these perceptions are often distinguished between perceptions on internal phenomena or external phenomena. There are often specific sensors available for measuring or sensing internal information and external phenomena. And what's very important here is that the agent exploits this knowledge to react appropriately, to react to changes either in internal or in the external state. What is also important to understand is that self-awareness means many different things in many different contexts. So also one objective of this lecture here is to try a little bit to clarify or helping to unify the terminology used in self-awareness. And also what I mentioned in the beginning is that I'd like to focus on self-awareness in a computational context. So also all the main concepts are originating from psychology or cognitive science. My focus here is what does self-awareness mean in a computational context? And the key objective here is we want to increase the autonomy of a system, the autonomy of either a single agent, a robot, or a network of agents. And so we would like to be able to learn and exploit the models of itself, of the agent itself, and the learned model about the state of the environment. And we also want to act in accordance with some goals, high-level goals. Typically, these high-level goals are explicitly or implicitly given to the agent. And as we'll see, many of the techniques are already available, known methods and algorithms from the different disciplines. So this is also, I think, a good argument, a good motivation for trying to understand the meaning and the interpretation of self-awareness from the different concepts. So what you see throughout these slides here is, and also the lecture notes are available, there are many references included, and these references should provide much more details than I can cover in this lecture. When we talk about self-awareness in a computational context, we often start with some kind of computational framework, with some architecture about the specific concept, the specific implementation we want to achieve. So what you see here on this slide is one of such an architecture. We will see different architectures throughout this lecture. What is common here is that we'll have aspects or parts of these architectures which are responsible for analyzing the observations, for deriving learning models and reasoning with these models, and eventually also for the decision making, how to derive decisions for this agent. And typical inputs are naturally the sensors in order to understand phenomena and the actions or actuators. Sometimes we have specific inputs for the goals, and if we talk about network of autonomous agents, then we also need networking interfaces for exchanging data. There are different approaches, many different approaches available. The key distinctions are here about what are the levels, what kind of data we process, what is the abstraction level we achieve in this architecture. What is the a priori given or innate knowledge given to the agent? Okay, do we have a rich knowledge available, or do we have very limited initial knowledge and capabilities available? And naturally, there are also quite some differences with regard to the applications and the application domain. As I already mentioned, an important aspect of self-awareness is the representation of the self, so the information about and the models about the agent itself. What we often see is a clear distinction between internal and external perception and actuation. So internal perception helps the agent to understand the internal state with regard to the current mission, and this is often referred to as propriation or proprioceptive sensory input. And another important aspect of these architectures is also about how can we reason about this decision making, about their own decisions, their own decision making. Are there what are the specifics to reach decisions and to act appropriately? Okay, so we can already see many examples where self-aware concepts have been deployed or have been implemented. So this is just an incomplete list on applications where some concepts of self-awareness have been implemented. So they range from hardware components in order to perform some reconfiguration on the hardware based on changes in the internal state or the environment, to software systems, to networks, to robots, or even to acoustic perceptions or sound generations. I do not go into the details about the different applications. I just refer to the special issue in the proceedings of the IEEE, where many of these applications are described in more details. And so I'd like to briefly summarize and give an outlook about the rest of the talk. Okay, so after this brief introduction, I will discuss briefly key concepts about self-awareness. So I'll talk about architectures, I will talk a little bit about models and capabilities. And these self-awareness concepts, they cover or they range from biologically or human consciousness models, biologically inspired models, to more purely computer science-driven approaches at a more abstract level. I will also cover two examples about the concrete implementation of self-awareness techniques. And as I already mentioned, I will also summarize a few important challenges. Most parts of these presentations are based on two sources. So the first one is this special issue in the proceedings of the IEEE, which has been published about 1.5 years ago. And also there has been a large European project on self-aware computing systems. And one of the major output of this European project is a book on self-aware computing systems. Okay, so let's start with the first part about concepts, architectures, models, and capabilities. And we'll discuss them, as I said before, starting with some kind of neurobiological view over some signal-based architectures, and eventually to some computational-driven or computational view on self-awareness. Before we do that, let's spend 1 or 2 minutes on some key terminology, which we often find in these architectures. Right? So a first first important terminology is the concept or the idea of private and public self-awareness. So this refers to how does an agent obtain knowledge. And here, if this knowledge is about internal phenomena via these internal sensors, in order to understand the internal state of the agent, this is referred to as the private self-awareness, the private level of self-awareness. On the other hand, if we are concerned about external phenomena, what's going on in the environment of the agent, this is referred to as public self-awareness. Another important terminology is about levels of self-awareness. So these levels of self-awareness, they describe different capabilities for how to obtain the knowledge and how to exploit the knowledge. There are different names for these self-awareness levels. Naturally, you need to look into the details of the specific approach. So what is written here, stimulus, interaction, time, goal, and meta self-awareness are the levels that we have been deriving and also inheriting from human or psychology-driven levels of self-awareness. So stimulus-driven self-awareness, stimulus self-awareness is the most or the simplest one. It's basically just reaction. So we react to specific stimulus. Whereas meta self-awareness is the most complex level, where the agent is really capable to reason about its own self-awareness. And what is important here is also that this different knowledge and different in order to reason about the self-awareness, we need to do this reasoning in real time, while the agent is in operation. The third category here is collective self-awareness. So this is often referred to as the capabilities of a group of agents, so a network of agents. So a particular challenge here is that there is no central point where all the knowledge, all the models are acquired or stored or retrained. This knowledge, these models may be distributed. And so reasoning, acquiring knowledge and also reasoning based on this knowledge might be quite challenging. And self-expression, the fourth category here, is a specific term concerned about how to make decisions. So it's about how specific behaviors can be achieved. And this is used in order to make the difference to knowledge obtainment more explicit. Okay, so let's start with some specific concepts, some specific architectures. So what you see here is a neurobiological inspired self-aware system. The key idea of this approach is to exploit neurobiological principles that can be deployed in an autonomous system. Right? So what you see on the right-hand side are a typical architecture of an autonomous system, what we see in robotic applications often. So we have low-level control, basically responsible for motor control and very short-term control issues of the robot. Then we have this intermediate control, which is more related to self-maintenance, self-monitoring behavior and basic behaviors of the robot. And then the high-level control layer is related to planning, reasoning, and navigation. What Chiba and Grigmar have done is they investigated various neurobiological principles, either from cells or from more complex systems, and try to map them to these levels. Right? So we see this on the left-hand part. We see these sensory and motor primitives, which correspond to these innate behaviors the reflexes, and they are typically available in biological systems in order to do some preferences or avoidance based on some values. Okay, based, for example, based on some, but there's no learning implied. The middle layer is concerned about maintaining stability of the system. And here in biological systems, we see two key processes, concurrent processes. These are homeostasis and allostasis. So homeostasis aims to provide stability through constancy, and allostasis aims to perform some kind of predictive control of physiological conditions. And these are important for self-monitoring. And also an important aspect of this middle layer in biological systems are neuromodulation and value systems. So these are important signals to derive contextual information. In biological systems, these are often feelings. And these feelings can then trigger specific behaviors or changes in the behavior. And then on top, we see the cognitive control of a biological system, and this is also about predictive control, which requires some kind of models. We have here some attention systems deployed in order to focus attention based on and to be more resource efficient and to focus on salient stimuli instead of just noisy stimuli. And here it's critically that the biological agent is able to learn and retain knowledge. Another concept, another model here, what you see here is the Mazis human conscious model. So this is a very famous model. The key idea here is that Damasio wanted to develop a model of the human nature of consciousness and the construction of the self. Okay, and this human consciousness model is based on real neuroscientific data. So what you see here is in this architecture is that this autobiographical memory is one of the key components. And this is used to store models about the learned experience, the learned episodes. And these episodes are encoded by some derived neuro vocabulary. And these are always specific pre-processed data, either collected from exteroceptive sensors and or proprioceptive sensors, and they are time dependent. And Damasio refers to these information units, these abstracted information units, dispositional units. And what's important here is these dispositional units are always contextualized. So exteroceptive unit is contextualized to a proprioceptive unit in a timed manner. And what you can do, or what can be modeled here with this approach is that this approach of representing these episodes can be abstracted also in a hierarchical way, so that we can establish multi-hierarchical representation of the episodes model. And then the other important aspect here is this autobiographical self, which is a unit which provides capabilities for comparing stored episodes or models of episodes with current episodes, with the current experience, with the current observations. So what this autobiographical self needs to be able to do is it needs to be able to derive inferences from the models, from the stored models, and also to detect discrepancies. We'll talk a little bit about these two important capabilities later on as well. Another also famous approach or architecture about self-awareness is Akins cognitive dynamic systems. So the key idea here is to provide or to develop a computational framework of neuroscientific observations from an engineering perspective. So what Akins CDS is a Bayesian, is providing a Bayesian framework in order to model the self-awareness principles at multiple layers. So what you see here is the key components. These are the perception, the cognitive perception units on the right-hand side at multiple levels. On the left-hand side, you see the cognitive control unit, and you see some kind of interaction between these different layers of these units via this probabilistic reasoning machine in the center. And the interaction are based on these abstracted data units, and the errors between the current perception and the models, the probabilistic models of these units. So the cognitive control basically it then performs and generates the output to these lower levels and to the agent actions at the bottom layer. And what this does, it eventually is that it instantiates this perception action cycle. This what we see in many of these robotic systems at multiple layers. It's also important to note that here there is no proprioceptive data in the original model. There's no proprioceptive data available. Akins distinguishes some internal strategies which can be related to some of these proprioceptive data ideas. Okay, then another approach is, for instance, BDS, Bayesian dynamical systems. So here the key idea is to establish links between neuroscientific observations with well-known computational models. And the computational models Friston is using are Bayesian dynamical systems. These are the computational tools. And this relates some kind of statistical mechanics with optimization with Bayes filtering. And an important concept Friston uses here are these generalized states as the basis for this filtering. These generalized states are kind of a vector of the random state, and its derivatives up to a given order. It's not just the first derivative, but derivatives up to a given order. And another interesting idea, for instance, exploits here is the free energy principle. So this is also a famous principle, and this is used as the optimization criteria for either discovering new models from given experience or to issue the proper actions on given inputs. Okay, so what we've discussed so far are approaches which are mainly based on cognitive or neuroscientific context. I'd also like to introduce briefly some concepts from more computer science, from a more abstract view and a more engineering or design approach from the computer science community. So what you see here is a reference architecture for engineering self-aware system. Here, the key idea is, as I said before, to propose this generic framework and also to provide kind of design patterns for implementing the different levels of self-awareness. So what you see here is also in the self-awareness block, the different levels depending on the capabilities, and based on these capabilities, one can apply different design patterns in order to realize specific implementations. Also, what is explicit here is this distinction between external sensors and actuators versus internal sensors and actuators. And there's also this specific meta self-awareness block, which allows reasoning about its own decision making. And this allows to explore trade-offs between the different decisions an agent could make. And finally, also from a kind of historical perspective, there is this MAPE-K architecture, which has been proposed quite some time ago. And the key idea of this MAPE-K architecture was to perform self-management and self-configuration of complex software systems during runtime in order to optimize the various objectives of this IT system. It's composed in different activities or capabilities. So in order to be able to configure the software, to optimize the software, to perform some healing, and also to perform some protection of the software infrastructure. And what you also see is that we have this kind of constant cycle executed by the autonomic manager in order to monitor the software component, to analyze the current state of the software component, to plan new configurations of the software component, and actually also to execute these plans. And these are and all these steps are based on this knowledge and available knowledge. So the MAPE-K architecture implements a control loop for software systems. And also in order to get feedback about the executed plan, it adopts ideas from reinforcement learning. But it's very clear that this architecture, there's no direct link to biological or cognitive processes. This is a pure artificial agent architecture. So when we analyze these different software architectures, we can draw some observations. No? So the first observation is that the architectures are quite diverse naturally, because they have different ideas. They come from different fields, different backgrounds. And also there are quite some differences about what knowledge and what capabilities are available. So the last architectures I provide, they have quite some high expectations and high requirements about this initial knowledge and the initial capabilities, whereas the biologically driven approaches have much simpler assumptions about initial knowledge and capabilities. And naturally also interpretation of sensor data and the actuating of the systems might be quite diverse. There are differences in the representation about the self. Some are really very explicit here. Some of them represent knowledge about the self on these derived models. And for example, Akins model has no real distinction between exteroceptive and proprioceptive. sensory data. What we also see is that learning capabilities are fundamental. Okay, basically in all models, we see some requirements for learning. Some of the architectures are very specific about what kind of learning are implemented, how this learning is realized. Some of them are more open and are more vague about this. And another important aspect here is that creating new models, right? Establishing new models when some discrepancies between current models or available models and current observations are available becomes very important, and also explainability is a big issue. What we also see is that typically the data and the reasoning is organized in a hierarchical way. Right? So similar to that is also kind of an overview about key capabilities of a self-awareness agent. So there is some initialization necessary. So we need to describe and we need to define what is the initial knowledge, what are the initial capabilities of an agent, how can an agent start to build then its own memories and its own models. We need some mechanism for storing and retraining information, the experience. We need to be able to exploit the models in inference. Okay? So we want to make predictions about future states based on our acquired knowledge. And then important steps in these self-awareness architectures is the capability to detect abnormalities. So to recognize observations that cannot be explained by the models, by its memories. And when such a situation is present or has been detected, we would like to be able to generate new models that encode the previous experience and the predictions that are supported by the current observations. So we want to build new models, and these models are then exploited for the decision making and influence the decision making. Okay, so let's talk about some implementations or some examples of implementations of these self-awareness concepts. So the first one is an idea to realize self-awareness capabilities based on a signal-based Bayesian framework. And a key focus of this approach is that we want to support hierarchically and multisensory filters. So it's some kind of an extension of dynamic Bayesian networks, of the ideas of dynamic Bayesian networks, like in for instance model. And what you see here is that these models have two different TPN implementations, some hierarchical TPN implementations. One for a proprioceptive model, which allows inferences at the sensory information with regard to its actions and the internal states. And on the right-hand side, we see exteroceptive dynamic Bayesian networks at multiple levels in order to allow inferences of sensory information with regard to the sensed environment. So we have this multi-layer approach where the lowest level corresponds to the observations. The central layer corresponds to stationary states, or stationary states of the agent, or the perceived data with regard to the state of the agent. And then we have this abstract layer, which corresponds to changes in this state. And the implementation of this dynamic Bayesian approach is done with Markov-Chain particle filters. And then what you also see here is that there is some coupling possible and some coupling exploited between proprioceptive and exteroceptive models in order to realize context-based inferences. So to realize inferences based on what is the current state about my internal model based on what I currently experience from my exteroceptive sensors. This has been implemented, or this has been assessed in an autonomous vehicle setup, a robotic application, where the autonomous vehicle is executing basically a reference task, so circling around, and then these reference tasks are conducted. However, there are some disturbances, so where the vehicle must bypass some obstacle. And this has been implemented with different sensory input. So proprioceptive input based on steering information, steering angle, power information, and the rotor velocity, and vision. So first-person view as exteroceptive sensor. So what you see here is just an example below, just an example of this of these different sensor inputs, and what is also marked here in this chart is situations where we see then some abnormalities based on these disturbances. So how have these different capabilities been implemented? So in particular, the implementation, inference, and abnormality detection. So for the proprioceptive model, we employed random walk dynamics as a base model, and this simple dynamical model is then clustered based on some, in order to derive some kind of regions where we see static behavior. For the vision input, the situation is more complex because we have a more complex input data. So here, chants were used to codify the state of the image processing based on the optical flow, and we separated basically linear motion based on the gain codification. Inference was performed at the continuous and the discrete level, so monitoring continuous state changes or changes at regions where linear movement was conducted. And as for the abnormality detection, we deployed a simple distance metric, so Hellinger distance metric between the prediction and the observation in order to distinguish whether we are consistent with the reference task or whether some abnormality can be seen. What also has been investigated was model creation, and here the identified errors were used, and also then later on the free energy concept were used to derive new models based on the existing models of the environment. Okay. So I quickly go to a second approach. So here the idea was to investigate self-awareness or deploy self-awareness technique in a collection of agents. So here we want to basically perform decentralized resource-aware network-wide analysis, and we do this in a camera network. And the idea here was to perform autonomous multi-objective tracking. So each camera is able to perform some tasks. So the initial knowledge is much higher than in the biological-driven approach. So the camera is able to do some object detection, object tracking, and the control is the handover of this tracking from one camera over the other. So the key decisions for this network or for the cameras in this network is when to track a specific object and when to initiate and hand over to, so the tracking handover to another camera, and whom to hand over this object. So this idea is shown here on this figure. So you see just 4 cameras, and the yellow dot represents the object of interest, and the purple camera is the one which is responsible for the tracking. And some point of time, the object is about to leave the field of view, and then this camera should initiate basically this decision about whom to hand over. So this is done with an virtual market approach, and then a specific camera takes over. Okay, so we implemented this with this computational architecture. We followed the design pattern I just sketched in one of my previous slides. So what you see here is the blocks for the self-awareness and the capabilities of the self-awareness, the decisions which the self-expression component is able to make. So object handover and strategy selection, also whom to hand over, and also the interaction between the cameras over this networking interface. Okay. So in the interest of time, I do not go into all these details here about this the implementation of this control strategy. What's important, as I said before, what's important to understand is that each camera should derive by itself, by analyzing what's going on in its neighborhood and what is the current state of it, to derive these local decisions. So when to initiate an option, when to initiate an handover, whom to ask for handover, and when really to perform this handover. As I said before, this has been implemented in a virtual market based on utility functions. All right. So by observing this trading behavior, we can learn also the network topology. But what I really would like to stress and so is about the overall performance of the network. All right. So we have implemented different strategies. So either we perform this option initiation actively, so at periodic intervals, or passively, only when an object is about to leave the field of view. So then the camera itself triggers this. And the invitation, whom to invite, there were 3 different strategies. So we can either broadcast the invitation to all cameras, then this will introduce a lot of communication effort, or we could limit the invitations to based on this probabilistic information we learned from this topology graph. So there were 2 strategies. Either we exploit some probabilistic approach, or we also implement some thresholding. So the strategy we select depends, has an influence on the overall performance. And what one can see is that there is a trade-off between the overall performance, so the overall utility of the system, and the effort. And the effort is just represented here from the communication perspective. So what you see here is, depending on the setup and the scenario, we can identify a Pareto front, an emerging Pareto front of these 2 objectives, utility and communication. Here, all cameras follow the same strategy, so either passive step, passive snooze, or active broadcast, which introduces the most effort. However, when we let cameras learn individual strategies, so we have a heterogeneous strategy, we see much more flexibility and even better results. So in this representation, better would mean more left and top than the previous point. And eventually, we can also do online learning, where we learn strategies while the camera is operating. And here we see the best performance, the best overall performance. This is indicated by this colored blobs. Okay, so I want to wrap up my talk and my lecture with some challenges I see and for self-aware computing systems. So the first challenge is, how should we design self-aware systems? This is what we currently see is that mostly we see case-by-case design approaches so far. And these case-by-case approaches, they strongly depend on the complexity of the self-awareness models and the type and dimensionality of the data, and also the complexity and the objectives of the agent. Ultimately, we would like to come closer to some kind of theory of how to engineer self-aware systems. So this is not an easy task. Maybe one approach could be to collect best practice examples, to analyze benefits and limitations, and proposing, understanding, analyzing design guidelines and patterns. Another challenge is, so this design challenge, the previous design challenge is mostly related to individual agents. So the situation becomes even more complicated when we think about collection of autonomous agents. So and here we have challenges about decentralization of knowledge, decentralization of decision making, and also communicate what to communicate and how to communicate information or decisions between the agents. Another challenge is, how can we guarantee specific behaviors, or how can we avoid specific behaviors and a self-aware agent may take? So when we deploy these models and when we apply this model construction and this model adaptation, we face drifting problems, and we face behavior generations which we actually do not know upfront. Right? However, designing an agent that a specific behavior is guaranteed might be important for safety and resilience of the system. Or the opposite is that we can guarantee that specific behaviors are avoided. Is important for this kind of for safety, resilience issues. So we would need to come up with some specification of models and behaviors. But this kind of formal verification of models and behavior somehow contradicts the concept of self-awareness. So I think this is a very important challenge. And in order to deploy self-awareness in a computational context, this needs to be addressed. Another challenge relates to the cost of self-awareness. So self-awareness doesn't come for free. So we need these capabilities. We need to understand all this reasoning, and also we would like to estimate the system performance and properties, so such that we can better estimate the resource usage and the cost, but also reliability and safety, and also the overheads and the trade-offs, the benefit between the additional self-awareness capabilities, the potential benefit. And such an estimation of the cost is also the basis for making online decisions when it comes to what self-awareness capability should be used when. So cost and trade-off of self-awareness is another challenge. And finally, I do think that the challenge on how to earn trust in self-awareness, in particular when we apply self-awareness and these robotic systems in society, is a precondition to be applicable, because trust is essential for us as humans, and the autonomous systems must be designed in a way that it understands and follows all the social norms, including morality, ethics, and other conventions, and earns trust of the others in the society. So finally, to be accepted and strengthen our society, the autonomous systems must show that they're worthy of trust according to social norms. And so this comes now. This brings me to the conclusion of my talk. So what I wanted to convey is that an overview about different concepts and different terminology of self-awareness, and to increase your interest in this concept. And because I do think that self-awareness may become a fundamental principle with the potential of becoming an enabling technology for various autonomous systems. However, as I just indicated, there's still a long way to go. Okay, and so I'd like to thank you for your participation, and I'm looking forward to your questions.
Thank you very much, Professor Rinner. It's really a very interesting topic, and your lecture was fascinating, so I hope it's going to motivate new researchers. Questions, please. Pablo, just voice up your question.
So hi, Bernhard, thank you very much for the talk. Sorry I was a little bit late. I was looking forward to your talk a lot. So I've been working in this field in self-aware robotics for some time already, but I never said the word self-aware. I never put it in my papers. I never mentioned, because I'm working with neuroscientists, and self-aware is a concept that forces you to be to have consciousness, and robots, they don't. And that's why I love to see that you're using in a different way from the engineering perspective, something that I always try to avoid, but suddenly it is there, right? So yes, I really like that. And
yes. Okay, so is your question
No, I was trying to contextualize myself, because I'm also between neuroscience and robotics. Mm-hmm. So my question will be about adaptation. I mean, I know your work, and only the last 2020 paper starts to be closer to what I'm doing with the robotics. And as you know, if you have played with those algorithms, there is a conflict between adaptation and actually knowing what is your identity, or to have this kind of self-reflection. Because if you adapt so much, then you don't have error detection, for instance, right? So adaptation is against all these kind of error detection, self-identification, and self-recognition. So
I'm sorry, I didn't get it. Yeah. Okay, now go ahead.
So my question will be, how in the work that you presented from multisensory integration with these vehicles, how you define? Can you specify more how you define the goals? And do you have any trouble with the balance between adaptation of the algorithm and its ability to actually be self-aware?
Okay. So there is about this approach described. So the first case study. So here the key idea is really to apply self-awareness principles more or less from this basic capability, starting from these basic capabilities. As I said before, being able to understand and initiate the models, being able to derive abstract models which which are generative, so which we can construct, but we can also use for inference. And then based on these inference capabilities, how can we use these inference capabilities in order to detect discrepancies, abnormalities, and based on these detected abnormalities, use these errors basically to feed back to the model generation process. So the key concept here was really on the key ideas. And as you know, there is much work going on here, and in particular, I'd like to mention the work from Professor Rigazzoni at the University of Genoa, who has been very active in this domain and applied different principles and different methods in order to develop these basic self-awareness capabilities further.
Yeah, but let me just ask the last one more technical. If you compute the inference of a model-based learned aspect, then of course you can do it. But if you allow it to adapt, then if, for instance, if you minimize the free energy, you will never, you have to know where are your limits of your boundaries of the system in order to actually understand it, because if not, just by minimizing the free energy, for instance, you only get adaptation, but you will never be able to understand what is the goal of the system. This is what I was afraid.
Yes. So understanding the goals of the system is definitely challenging with this approach. Yes, I agree.
Thanks so much, Professor.
Are there any other questions, please?
I have a question, if you can hear me.
Yes, sure.
Yes.
Go ahead.
Excellent. So I guess to contextualize where my question is coming from.
Just present yourself because I see just an MDP. So what does it mean, your name, and where do you come from?
All right, cool. Yeah. So my name is Martin. I'm in Canada at the University of Toronto. So we're working on kind of like neurobiologically inspired autonomous systems for robotics. So I had a question, which is more going to try to contextualize the literature and contextualize the work. And I guess kind of be like where you are right now. Like, do you feel like, or do you think that a lot of this work comes and inherits the work of like cybernetics? And do we have, and especially second order cybernetics, and do those ideas, which are really old and almost like kind of vestigial now, do you feel like they have any sort of like promising avenues to address these contemporary problems? And for instance, like as you're describing like internal versus external sensors, what comes to mind is like Maturana's idea of autopoiesis and a boundary, but you didn't really speak specifically on boundaries, but one could kind of like imagine that the set of models that are being retained is the boundary. And so can you speak on kind of the history, like can you speak on like kind of where we can look to for answers to these challenges?
Yeah. So I think that's a good point. So a potential source for looking really on these issues is I'm not sure whether you're aware of this special issue of the proceedings here, which are now listed. There are some papers addressing the different modeling approaches and also the historical perspective on them. And naturally, there's a huge body of literature out there from neuroscience-based approaches, neuroscience-based techniques. And honestly, so my background is really from computational engineering. So I'm not a neuroscientist. So probably we need to contact neuroscientists and neuroscientists with this background on how to model and how to deploy self-awareness as a more appropriate source for really getting inside information here.
So
I'm sorry, so I'm not probably giving a satisfying question or to answer your questions in a satisfying way.
Oh, not at all. But I guess to follow up and like to kind of wrap that up, so it's like we need to like look to the neuroscientific biological domains,
yes,
and then
so,
try to implement those in the computational straight technical field.
I think what could be really a worthwhile initiative, and there are already some of these larger projects and concepts out there which tries to bring together really the different disciplines and helping to understand each other better. Also, what I do think is important to clarify the terminology much better, because it's not so easy to understand the concepts from the different fields, and then developing new approaches and new techniques.
Well, in the last, let's say, month or so, I had an in-depth interaction with a neuroscientist that he is retired now, and it was really difficult for me to grasp their language. First of all, because their definitions were quite vague, and they had multiple meanings, and being far away from this community, it certainly we have to interface better with them and try to define some things and use them in a consistent way. So Bernhard tried his best in this lecture, but it's a huge topic.
Yes, I fully agree. So we also analyzed and worked together with psychologists, and it's the same here. So there's a huge body of work out there, but understanding understanding the language is not so easy.
There is a question by Mr. Fauzi Bouali. Can you please voice this up, or do you want me to read this for you? The question is whether advanced communications have a role to play in autonomy.
I'm not sure I got the point. So what is meant by advanced communication?
I suppose 5G.
So I think 5G would be just a technical mean for realizing communication between agents. So from this perspective, so it's naturally it depends on the application in mind. Naturally, it depends on how much data and what are some kind of the temporal aspects of the communication are relevant, but conceptually, whether it's 5G or another technical communication network, I think is not a core question.
There's also another question by Mr. El Bakuri on the relation between self-awareness and pervasive computing and autonomic networks in chat.
So the question is, what is the relation between self-awareness, pervasive computing, and?
Yes.
Okay, so the point here is that in pervasive computing is one approach, or is one idea to integrate or deploy computing techniques in many of our everyday appliances or everyday systems. What we'll see nowadays is that these everyday appliances get smarter and smarter. They become more autonomous and autonomous over time. So from my perspective, and since I'm working in pervasive computing, self-awareness is one concept or one idea on how to realize and how to make systems more autonomous. And so that's from my perspective, and this is just from my background, the link between pervasive computing and self-awareness.
Is there a last question, please? If there's no more question, then we can call it a day. Professor Rinner, thank you very much for your very interesting talk, and let's hope that this is a very nice topic for future cooperations. Thank you.
Thank you very much. So